Okay, so the limit as x approaches 1 from the left, going from the left-hand side, is 3. The limit from the right is also 3. So the limit itself is 3. Easy. Not so easy. Okay, the limit from the left is -1. Limit from the right is -2. The limit itself does not exist. Why? The limit as x approaches 1 from the left of f of x does not equal the limit as x approaches 1 from the right of f of x. That is why the limit itself does not exist. And what type of discontinuity is this? It's a jump discontinuity. Okay, to make this a little easier, this is A, that's point B. And sorry, continuous is misspelled. Okay, one-sided endpoints are a little different, but almost the same as any other point along a curve. With endpoints, you use right and left-hand limits. The limit as x approaches a from the right of f of x is equal to f of a. Therefore, it is continuous at x equals a. So at the left endpoint, it is continuous. The limit as x approaches b from the left of f of x does not equal f of b. F of b does not exist. Open circle at the end of the line. Therefore, and my bad, should be therefore. Therefore, not continuous at x equals b. So it works for the left endpoint, but not for the right endpoint. The difference between endpoints and any point in between the endpoints is that the limit has to work. At endpoints, you can only use a right-hand limit or a left-hand limit. But the left and right-hand limit also have to equal the coordinate itself. The coordinate actually does not exist. So actually, this part here is irrelevant. This part right here, that technically is irrelevant because I have to have three things, and the point itself not existing is one of the three things it violates. I have to have a limit, I have to have the point, and I have to have the point and the limit be the same. The point and the limit are not the same, but then the point itself doesn't exist. So two out of the three things don't work.
I know. What did the three circles?
Therefore, because I would rather put three little dots than write out an 8-letter word. Mathematical symbolization. Okay, here you go. Write it out. Okay, highlights. If f of x is continuous on the closed interval from a to b. So first condition, it has to be a continuous function between two endpoints. Has to have endpoints. It's not continuous forever, but only in a particular range. And second condition, there is a point m that is greater than or equal to f of a and f of b, or less than f of a and greater than or equal to f of b. Basically, m is between those two y coordinates. And why do I have both of them? Why do I have both of those conditions stated? What? It has to be in the interval, but why not just use one interval? Now, I don't know if f of a is smaller than f of b or not. The first one assumes that my y coordinate for my first coordinate is less than my y coordinate for the second coordinate. It could be the other way around. Basically, I'm covering my bases on this and saying that I've got a point between the two y coordinates, no matter the relationship between the two y coordinates on the end. Whether the one on the right is less than the one on the left or vice versa, I don't know. This covers my bases. But it has to be between them somehow. So this is an easy way of stating that it's between them, no matter what their relationship to each other is. It also covers the 2 points being equal, because that can work as well. If those two conditions are met, then everything is an if-then in a theorem. If this is true, then this is true. That's what all theorems are, if-then statements. If these conditions are met, then this is true. Then there is a C. There is a C such that C is between the two endpoints and f of C is equal to m. This, remember, this is a very powerful statement. It says, if I have 2 points connected by a continuous line, and there is a y coordinate between the two y values, there has to be an x coordinate between the two x endpoint x values, where that x and that y, where there has to be a point that exists between them. This is an extremely powerful statement. This is one, like I said, if you go from, if you have, do I have a 0 existing? Well, if my y coordinate for one endpoint is positive and the other endpoint is negative, what has to happen in between? There has to be a 0 between the negative and the positive at least once. At least once. And there's an x coordinate that will make that equation 0. At least once. It could be many times, but it has to happen at least once. Okay? There has to be at least one of those. It's a very powerful statement that, hey, if I know this point and I know that point, there's got to be something in between. There's got to be something that works in between. And that counts for giving me at least 1 point. But that also means that every single y value between the first y value and the second y value is somehow produced by that function by some x coordinate in between at least once. So if I go from 5 to 10 on my y coordinates to the end, that means 5.1, 5.2, 5.3, 5.4, every single possible coordinate, every single value between 5 and 10 is somehow produced by that equation between where the first x coordinate and the second x coordinate. At least once. Could be more than once, but at least once it happens. Okay? And that is a powerful statement saying, hey, it exists, it happens, it takes place. We know it can do it. That's an important statement. Because if you don't know, it may never happen. We can prove that it does happen. We can prove that it does happen. All you have to do is say it's continuous, and I have these two endpoints. That means every other number between those two endpoints is produced. Now, that's a very powerful statement there. What is the right end behavior model and the left end behavior model for the function f of x equals e to the x cosine x. Okay. Right end behavior model happens as x goes towards positive infinity, because it's what's happening as we're going off to the right. And that would be f of x is equal to e to the x. Because e to the x gets extremely large, but the cosine of x just goes between 1 and negative 1, 1 and negative 1, 1 and negative 1. At some point, adding or subtracting 1 or some number in between them is not going to make any freaking difference to e to the 10 million. E to the 10 million is this gigantic number, and adding or subtracting 1 from that is irrelevant. Okay? So my end behavior model is e to the x. So my right end behavior model. My left end behavior model is what happens as x goes towards negative infinity, which would be cosine x. Because although cosine x will never be larger than 1 or smaller than negative 1, e to some extremely large negative power is essentially 0. And if I'm adding essentially 0 to anything else, that essentially 0 makes no difference whatsoever. Okay. What is one of the most useful things to use right and end left behavior models for? What would you want to use them for? Well, this is a big one. I might change the test if I don't get a good answer on this one. What are right and left end behavior models extremely useful for? Finding horizontal asymptotes. Because your horizontal asymptotes are only going to work out at the extremes. And right and left end behavior models are what's going on out at the extremes. So if I look at this one here, do I have any horizontal asymptotes? E to the x grows without bound, so I do not have an asymptote to the right. And then the cosine, does the cosine of x actually have an asymptote? No, it varies. It's contained within plus or minus 1, but it does not narrow in on anything. So the cosine does not have asymptotic behavior. So I do not have any horizontal asymptotes for this particular function. But end behavior models help you find horizontal asymptotes. They're also good when you're looking, when you're saying, hey, what's going on with really large numbers and really small numbers? Then I can use them just because I can ignore the crap in the middle. Okay. Do either one of these look like that around the origin? No. They look like that when you get way away from the origin. It doesn't take very long, though. Probably at about 100. Not even at 100. Negative 100. Because e to the negative 100 is like this teeny tiny little thing, makes no difference. E to the positive 100 is still this huge, giant number. So you can get out to 100, you know, the stuff in between doesn't make any difference. Oh my God, that was a hint. Okay, so let's do this. Start with the horizontal asymptotes, because it's easier. Okay, so the end behavior model for h of x is x squared over x squared, which is 1. Because when you're doing end behavior models of polynomials, it's just the largest polynomial power, x squared over x squared, that simplifies to 1. So the limit as x approaches plus infinity of h of x is 1. The limit as x approaches negative infinity of h of x is 1. Therefore, h of x has horizontal asymptotes at y of y equals 1. And notice I checked both left and right because they could be different depending upon the equations. Generally speaking, if you have a rational function, they're going to do the same left and right as far as horizontal asymptotes go. But if you don't have this, they might be different depending upon what's going on with the original equation.
So it would be what kind of equation?
You still just, all you have to do is just check the left and right. And because your left-hand behavior model and your right-hand behavior model will be two different things, that is a possibility that you have something along those lines. A graph, a very common one that I've seen where you have a graph of an equation, and I cannot think of the equation off the top of my head, but it would look something like this. I've seen ones like that. And they do, they have left and right, different asymptotes. Different asymptotes, going left, going to the right. It happens that way. There's an equation, I've seen that. Actually, I think we did a problem like that earlier. There's one of the notes. Okay. But there are ones that are like that. Okay. Usually, I think those are like roots or something like that, like cube roots, something along those lines. Okay. Now, for the more fun one, and I will have to scroll up and down on this one a little bit. So, for the vertical asymptotes, vertical asymptotes, we have to take the equation h of x and find where the possible vertical asymptotes are. X squared plus 8x plus 15 over x squared minus x minus 12. And what you want to do to that is you want to factor it. X plus 3, x plus 5 over x plus 3, x minus 4. So where are my possible vertical asymptotes? My possible vertical asymptotes happen at x equals -3 and at x equals 4. I have to consider any place where it's undefined. Now, for purposes of actually evaluating those asymptotes, remember, I can use a simplified version which reduces down to x plus 5 over x minus 4 for my evaluation. When I take the limits, because what do I have to do? To find the horizontal asymptotes, I take the limits as I go to positive and negative infinity. For horizontal asymptotes, vertical asymptotes, I take the limit as I approach these coordinates from the left and right. So the limit as x approaches -3 of h of x, I can actually use x plus 5 over x minus 4, and I can actually find the limit. It will be the same from the left and right. Put -3 in there, I get 2 over -7, right? So it's -2/7. No vertical asymptote at x equals -3. What is happening at x equals -3 though? It's a little hole in my graph because it doesn't exist. It's a little hole in my graph. That's what's going on there. So I did find an important point. There is something important happening there. And we will spend an inordinate amount of time looking for the important places in this class. That is an important place. Something is going on there. What's going on there in this particular one at x equals -3 is we have a hole in the graph. The original function does not exist there. It's kind of important to know when your function doesn't exist. Kind of important to know that. Okay? We will actually be looking for what we will call critical points. That will be the technical term, critical points. We'll be looking for those. Okay, now I need to do my limit as x approaches 4 from the left and right. The limit as x approaches 4 from the right. And I'm going to go ahead and put in x plus 5 over x minus 4. As I approach numbers slightly larger than 4, my denominator is getting smaller and smaller and smaller going towards 0. But if I put a number slightly larger than 4, it's going to be positive, right? And numbers slightly larger than 4 plus 5 are also positive. And this goes towards positive infinity. The limit as x approaches 4 from the left of x plus 5 over x minus 4. Same concept. I put a number slightly smaller than 4. This is still positive. This is now negative. These go towards negative infinity. Therefore, h of x has a vertical asymptote at x equals 4. Okay. You have to use limits for vertical and horizontal asymptotes. I will be looking for that when you take the AP test. If you have to find it by showing your work on a free response, I guarantee they will be looking for you using limits. I've never seen that, but that doesn't mean that they won't throw that in there at some point. Okay, they've done the last couple of years. They've really changed a few things up on me. Okay, here we go. Let's do the easy one first, and the one that everybody screws up because it is easy. The average rate of change is g of 4 minus g of 2 over 4 minus 2. Slope connecting the 2 points. So g of 4. 4 squared is 16. 16 minus 8 is 8 plus 1 is 9, right? Right? Yeah. And then put in 2. 2 squared is 4 minus 4, so I get 1. 9 minus 1 over 4 minus 2. That's 8 over 2, which is 4. Right? Right? Because 4 squared is 16. 2 times 4 is 8. 16 minus 8 plus 1. Okay. Now, here comes the fun part. Woo! The instantaneous rate of change is the limit as h approaches 0 of f of 3 plus h minus f of 3 all over h. That's what you have to use to find the instantaneous rate of change. So you have to use that. I don't see that. You get 0, zip, zilch, nada. Okay. So this is the limit as h approaches 0 of, and what was the function again? X squared minus 2x. So that would be 3 plus h squared minus 2 times 3 plus h plus 1 minus 3 squared minus 2 times 3 plus 1 all over h. Now I'm just going to do some fancy algebra. See, limit as h approaches 0. Oh, 3 plus h squared, that's 9, plus 6h plus h squared minus 6 plus, or sorry, minus 2h plus 1 minus 9 plus 6 minus 1 all over h. And let's see. The 9 and the minus 9 cancel. The 6 and the negative 6 cancel. The 1 and the minus 1 cancel. Look at that. And then I can reduce my h's. That h and that h and that h and one of the two h's there go away. So I have the limit as h approaches 0 of 6 minus 2, 4 plus h, which is 4. Yes?
Instead of plugging the 3 in for x at the beginning, can you just get the general form?
Yes. Did you do x plus h and x, and then plug 3 into your answer? That works too. So did you catch what he did? So what he did instead was he did the limit as h approaches 0 of f of x plus h minus f of x all over h, got that, and then plugged 3 into that equation. Then you got 2x minus 2, right? Yeah, that becomes 2. That is 2x minus 2. Plug in 3 into that. What do you get 4? So yes, you could do that as well, and that works fine. That actually works very well for many of the things. We're going to be doing that next chapter in terms of that. Okay, find the tangent line to f of x equals 1 over x plus 2 at x equals 0. Okay, so you're finding the equation of the line. You need 3 things. You need your x coordinate. You need your y coordinate. And you need your slope. Slope is equal to the limit as h approaches 0 of f of 0 plus h minus f of 0 all over h. Okay, because I'm doing it as I'm at x equals 0. So that is the limit as h approaches 0 of 0 plus h, which is h. So that's 1 over h plus 2. Put in 0 minus 1 over 2 all over h. Cannot put 0 in because I get 0 in my denominator. Doesn't work. So I need to make adjustments. I need to do some algebra first. So multiply by the common denominator. The common denominator is 2 times h plus 2. 2 times h plus 2. Okay? So, is the limit as h approaches 0 of 2 times h plus 2 times 1 over h plus 2. So that's 2 minus h plus 2 all over, bless you, 2h times h plus 2. Do not FOIL out the denominator. Do not distribute. Okay? So my numerator here, limit as h approaches 0 of 2 minus h plus 2 is negative h over 2h times h plus 2. I still can't put in 0 yet. However, these h's cancel, and I get negative 1 over 2 times h plus 2. If I put in 0 for that, I get negative 1/4. That's my slope, negative 1/4. So I go back up to the top. My slope is negative 1/4. Once again, that is your best friend. Point slope formula. Plug in your y coordinate. Plug in your slope. Plug in your x coordinate. And leave it alone. Unless it says to put it in another form, or unless it says to solve for this in terms of that, do not mess with it. Leave it like that, because if you start messing with it, you might screw it up and go from something good to something bad. I've seen it. I've seen it on my tests. I've seen it on practice AP tests. I've seen it on AP tests where I'm looking at sample answers. Oh, the kid had it right here, and they rearranged it and got it wrong. Because they added 4 instead of subtracting 4. It would really suck to lose a point on the test. It's really hard to get points on. Okay? Where 1 point can be the difference between a good score and a negative score. Bonus round! Where does y equals x cubed minus 3x have a horizontal tangent line? Okay. Okay. It'll be done. Okay, so here is what the question is asking you. Where is the limit as h approaches 0 of f of x plus h minus f of x over h equal to 0. This limit is the slope. Tangent line has a slope of 0. Where does this have a slope of 0? That's what it's asking. So 0 equals the limit as h approaches 0 of x plus h cubed minus 3 times x plus h minus x cubed minus 3x all over h. 0 equals the limit as h approaches 0 using binomial expansion. X cubed plus 3x squared h plus 3x h squared plus h squared minus, and actually I'm going to go ahead and get rid of this front parentheses here. If I can do it, yeah, there we go. Minus 3x minus 3h minus x cubed plus 3x all over h. Binomial expansion, distribute the negative 3, distribute the negative. X cubed, 3x, negative 3x. Let's see. H, there's one h, there's an h gone from there, an h gone from there, and an h gone from there. Nothing has not been reduced or canceled. Good. 0 equals the limit as h approaches 0 of 3x squared plus 3x h plus h minus 3. Let h go to 0. 0 equals the limit, or sorry, 0 equals 3x squared minus 3. When you plug in 0, 3x squared minus 3, x equals plus or minus 1. Plus or minus, let's have both possibilities. You want to know what we just did? Okay, what does a cubic equation look like? It goes up and goes down. Generally speaking, it's positive x cubed. It does the disco thing, going up and then going up and up. And if it's a good one, it's got 2 humps in the middle. This one is symmetrical. So this graph looks like that. It goes through 0. My other zeros are at plus and minus root 3. What we just did was we found that and that. The 2 horizontal tangent lines, they happen at the very maximum and very minimum of those 2 humps. We found where that maximum value and where that minimum value of those humps actually happen. Those happen at -1 and at +1. That's what we found. Foreshadowing.